Hi everyone, this is the notes and video for section 2.5, which is titled Postulates and Paragraph Proofs, but I'm going to refocus that paragraph proofs on something called two-column proofs. Okay, so in the past we talked about basic postulates about points, lines, and planes. That is, the undefined terms where the line goes on forever and does not have any thickness, point has no thickness, and planes go on forever and have no thickness. We're going to keep talking about postulates, some more of them involving points, lines, and planes, and we're going to talk about how to begin the process of putting together sound logical arguments, and we're going to formalize those in a method called two-column proofs. Okay, so what is a postulate? Or in this case, I've got also axiom. These two words I'm going to be using interchangeably. But it's a statement that we take as true. We're not proving it. We're just taking these statements as truth. And they're basic, usually, basic principles, let's call them. And they are things that we're going to use to build up a logical set of arguments, but we're not going to prove these building blocks, if you were. Okay. Theorem, on the other hand, is a statement that can be proven and must be proven. We must justify each theorem that we use. And we would prove these with logic and with justification on pretty much every logical argument we would make. And for example, we could say the Pythagorean theorem is something we've used quite a bit of. We can and will take a look at some very detailed proofs of why that's true, why the square of the hypotenuse equals the sum of the squares of the other two sides. When we try to prove a theorem, we will use our a series of logical arguments, and those would include postulates as well as other theorems. We can use one theorem to prove another theorem, and that's what Euclid did. As long as he proved each theorem as he went along, he was comfortable using them inside of another theorem. Okay, in terms of how we prove things, there's somewhat of an informal method, and that would be a paragraph proof, and that is just kind of describing your logic in the form of a paragraph. If you or I or anybody else wrote our own paragraphs on something, however, no one paragraph would look identical. I think we'd have an extreme variety of paragraph proofs. That's why it's considered informal. And we're not going to be doing much of this at all. So I really am not a fan of the paragraph proof. I think when we try to make logical arguments in that method, it becomes hard to interpret. So wherever from here on out on any of the worksheets or textbook work that we would do, if it asks for a paragraph proof, I'd like you to just consider the words or the goal to write a two-column proof. And a two-column proof is definitely more formal. We'll take a look in a moment what that looks like, but it's really more of a recording method, we'll call it, for your logical argument. So it's a recording method to kind of organize your logic. Okay? All right. Okay, so let's start to look at some more postulates regarding points, lines, and planes. So I've got several of them lined up with words, with some kind of diagram, and then we'll write an example. So here in the diagram you can see when two lines intersect, then their intersection is a point. and that's always going to be true. So an example here that we have lines S and T intersect at point P. That's what we have in the diagram. Whoops. Intersect at point P. All right, next one. And these two are both revolving, or involving, I should say, intersections. All right, in the next diagram, we have two planes that are intersecting. So if we have two planes intersect, then their intersection is a line. And I noticed on the last exam that this one is still a little bit hard for some people. So anytime two planes intersect, that intersection is a line because both of those planes are going on infinitely in both directions. And so they are not intersecting at a point. It is a line. So here in our diagram, we have planes F and G. I don't know if I could do the cursive G. Intersecting at line W. Okay. Okay, in this diagram here we have a line N with points P and R on line N. Through any 2 points there exists exactly one line. We could not find another way to draw another line between those 2 points. So here line N shown in the diagram is the only line through points P and R. Okay, now we have a plane K, and on it we have 3 non-collinear points A, B, and C. So through any 3 non-collinear, and that's the key right there, non, there exists exactly one plane. So over here we would say plane K is the only plane through, let's say, non-collinear points A, B, and C. And next we have a diagram. We have 3 points, P, Q, R, all on the same line N. And we know that a line contains at least 2 points. Even though 3 are drawn here, a line contains at least 2 points. And in fact, a line goes on forever, so it contains an infinite number of points. But at least 2 need to define that line. So in the diagram, we could say that line N contains points, and we could label them all. It contains points P, Q, and R. But we could just list 2 if we wanted to. Okay, next we have a plane K, and on it we have several points, and we know that any plane has at least 3 non-collinear points. So we could say plane K contains non-collinear points, and you could list 3 of them. Or we could list all of them, L, B, E, and C. And finally in this table we have a plane K, and on it we have 2 points, A and B, and a line M through those 2 points. And the postulate states that if 2 points lie in a plane, then the entire line containing those points also lies in that plane. So over here we would say in a description, points A and B lie in plane K. Oops. And M, line M. Oh boy, I'm not writing very good. Line M contains those points. A and B. Therefore, or so, M, that line M, lies in plane K. Okay. And now let's take a look at our first theorem. Actually, we've been using the Pythagorean theorem for a while, but let's take a look at the midpoint theorem, which we're already pretty familiar with. And then I want to look at the converse of the midpoint theorem. So the midpoint theorem states that if we have a segment AB and M is the midpoint of AB, then we can say the two segments AM is going to be congruent to MB. The converse of that is where we switch the hypothesis and the conclusion, but when we do that, we have to add a bunch of other words to it. So if points A, M, and B are collinear, and point M is between points A and B, so we have to know which one is in relationship to the others, and we're told that AM is congruent to MB, then we can conclude, sorry, this is an MB, then we can conclude if those two segments are congruent, then M must be the midpoint of AB. So it's just switching it up, and we can use either one of these. Both of these theorems are true. All right, and let's take a look at what I meant by the two-column proof process. So instead of you and I and everyone in the class writing wildly different paragraphs, we are going to start to do some very careful logical reasoning in a format called a two-column proof. It's called a two-column proof because that's basically what you're doing. You're setting up two columns. So what we're going to do is we're going to start, we're actually going to be given a conditional statement, something, or maybe some given information, which would be the hypothesis, and then a conclusion, which is something that we have to get to prove. The first thing we would always do is draw a sketch. We wouldn't even go over here to this two-column before drawing some kind of sketch of the given information. And it's really not just a sketch. I was just grading your Chapter 1 test, and I'm looking at some of the sketches, and it's not enough to just kind of sketch an angle or sketch a couple of segments. You really want to take the given information and mark everything that's congruent. For instance, if you have an angle bisector, you want to mark those two smaller angles to be congruent. You also want to mark the diagram with any measures that you're given, whether those measures are numerical expressions or more likely algebraic expressions. So I want to write down here and really emphasize this has got all the details on it, everything. So it's got all the details on it, and everything is marked. Certainly everything that's congruent should be marked with either the tick marks or the arcs, but you really want to get all of the information in the picture because it'll certainly help you a lot with the proofs. Once you have that step done, now you're going to set up your two columns, and the very first column is called your statements, and the second column is called your reasons. And the very first thing, all the given information that you've been provided, that's actually part of the hypothesis of the conditional statement. You're going to list everything. It may be one thing that you're going to list as the given info, or it may be several rows here of given information. And the reason that you would write that down, you would just say over here, it was given. So you would just write given or provided to you. That's justification enough. After your given is written down and organized, we're going to go through step by step statements of logic. So let's write that down, step by step. Logical statements. And these statements are going to be slowly getting to your ultimate conclusion. And your ultimate conclusion that we're trying to prove, that's what you're trying to prove. That information, what you're trying to prove, is going to be the last statement here in the left column. That means you've arrived at what you're trying to prove. And everything over here, every single statement that you make, it could be only one row that you needed, or it could be 10 rows that you needed. But every single thing from the given on down to the bottom is going to require some kind of justification, some kind of reason that allows you to write what you wrote. So no statement can be made on an ad hoc basis. Everything must have some kind of justification to it. Okay, so that was a brief description of what a two-column proof looks like, and we'll definitely get a lot of practice on doing that. All right, let's just take it a little bit slow and start to practice before we get into some big proofs. Let's practice using and understanding these basic postulates and axioms involving points, lines, and planes. And the way I'd like to do that is look at a series of statements, and I want you to determine if the statement is true always, sometimes, or never. And don't just put one of the three. Also explain your reasoning as to why you answered that. Okay, at this time I'd like you to stop the video and try to do these on your own. If you get confused at all, you can go back to the video. I'm going to continue on, go through each one, but I'd like you to try to do these on your own. Okay. Number one, if plane T contains lines EF, a line EF, and that same line EF contains point G, then plane T contains point G. Always, sometimes, or never. Well, the answer to that would be always. And what justifies our answer there is that we know by one of the postulates that we looked at that if 2 points lie in a plane, 2 points lie in that plane, then the entire line through those 2 points is also on that plane. So 2 points lie on plane, I'm just abbreviating or shortening as much as I can, then the line through those points lies on the plane. And I know this is a slightly different spin on it, because we've got this single point G here, but that point G, if it's on that line and that line is on the plane, then everything on that line is on the plane. Okay, number two. Line GH contains 3 non-collinear points. Well, that would be never. We know by definition that lines contain points that are collinear. Lines contain, let's see, my writing's a little messy, points that are collinear. Okay, number three. Plane A and plane B intersect in exactly 1 point. That would also be never. The intersection of 2 planes is a line, not ever a point. Always a line. Number 4, point N lies in plane X and point R lies in plane Z. You can draw only one line that contains both points N and R. That's always true. And the justification, there exists only one line between any two given points. All right, 2 points. Number 5, a line contains exactly 1 point. That would be never. Justification, let me rewrite that. There exists at least 2 lines. There exists at least 2 points through any given line. Number 6, non-collinear points R, S, and T are contained in exactly one plane. That's always true. So, through the justification, through any 3 non-collinear points is or exists exactly one plane. Number 7, any 2 lines L and M intersect. This is a little tricky. I'm not sure if you want to answer never. I'd be tempted to do that the way the statement is written, but maybe it might be a little bit clearer if we say sometimes. Yes, if L and M are on the same plane, they will intersect unless they are parallel lines. So let's say on same plane, parallel lines will not intersect, will never intersect. That's actually the definition of parallel lines. And the other case, let's say on different planes. On different planes, say if L was on one plane and M was on a different plane, and those lines are skew. By definition, that means that they're on different planes and will not intersect. In that case, those 2 lines will not intersect. So there are some exceptions, although on the same plane, most lines, any 2 lines that are not parallel will intersect somewhere. Okay, number 8. If points G and H are contained in plane M, then the line GH is perpendicular to plane M. And the answer to that would be never. If a line lies on the plane, it is not perpendicular to that plane. So in other words, a line on the plane has all points contained in that line on the plane. So I'll just say all points also on plane. In order to be perpendicular, that would be the case where a line would be going straight up and down at 90 degrees through that plane, and it would intersect at only one point. And that would be right as it's going through the plane. So that would have an intersection of one point, whereas a line on the plane has an intersection of the entire line. Okay, hope this helps. Thanks for listening.